Hi everyone. In today's video, we're going to look into how to create attention maps from Swin Transformer. Attention maps is another tool to just look inside the Swin Transformer. It's just like the confusion matrix, the training loss. It's another tool to measure the performance of your vision transformer. So we will look into how to train the Swin Transformer and how to create the attention maps after passing one image to the Swin Transformer. So let's get started. This is the official GitHub repository for Swin Transformer. I borrowed the classes from the Swin Transformer file, these classes, and I borrowed the model initialization from build file, basically this part here, and I borrowed the driver code from the main Python file, this file here. So I copied everything into a Jupyter notebook and I ran it on GitHub code spaces. So this is the Jupyter notebook, which I will link in the description below. Here I'm importing some libraries and I'm initializing some parameters for training. These are the Swin Transformer classes and helper functions. I'll go through these one by one. So the class MLP is just the very last layer of the transformer, the one that just before predicting the classes. After finishing from all the transformer layers, the Swin Transformer will call this MLP class to predict the classes. The window partition, it will take a tensor of size batch, height, width, channel, and it will return a tensor of number of windows into batches. So instead of images, it will return all the windows inside the image in the batch with the window size by channel. Because as you might know that the Swin Transformer does not compute the attention between all patches in the image. It computes that attention between patches within windows, and these windows will be shifted alternatively inside the transformer, and they got merged between layers. So the image will get smaller and smaller. So this window partition function will take a regular batch, the batch that you would usually see in the Vision Transformer, VIT, which is number of images by height of the image, width of the image, and channels, and it will retain the number of windows by batch. So it will be the, let's say, if we have two images and each of which has 8 windows, so this will be 16. So that is the first dimension in this tensor will be 16, and window size by channel. So this is done in this window partition function. The window reverse function, it does the reverse of this function. So it takes a tensor of size, number of windows by window size by channel, and it will return a tensor of size, the batch dimension, the number of images, and the height of the image, width of the image, and the channels in the image. Window attention. So this is in this class where the Swin Transformer will compute the attention between the patches within the window. So window-based multi-hit self-attention, WMSA control with relative position bias. It supports both shifted and non-shifted windows. So in the Swin Transformer, if you go to the paper and see the main architecture here, it has 4 layers, and each layer has a Swin Transformer block. If the Swin Transformer block has an even index, it will perform Windows multi-hit self-attention. But if it has an odd index, it will perform shifted Windows multi-hit self-attention. So this is what do they mean by it supports both shifted and non-shifted windows. Because here it accounts for the mask. If the mask is none, this means that the window is not shifted, so it won't add a mask. It won't mask out the attention values. The class Swin Transformer block is basically will determine if the shift size is larger than 0. So it will determine if this is shifted Windows attention or Windows attention, and it will basically do all of these things. So this whole box is the Swin Transformer block, and this purple small boxes are the Windows attention class. The patch merging, it will basically be performed between layers here. The patch merging here, patch merging, and patch merging. So it will downsample the image by 2. The basic layer is basically, it wraps up a Swin Transformer block, and if it checks if there is patch merging. The patch merging here is called, the parameter for patch merging is downsample. So this is this whole box here is the basic layer. Patch embedding is what happens at the very beginning of the Swin Transformer. This one here, patch partition. It basically runs a convolutional layer just to cut the image into patches. And the Swin Transformer class is basically which wraps everything into one model, and it predicts the classes at the very end. So here I'm initializing the model. I'm making some changes to the default parameters. I'm setting the patch size to be 4, and I'm setting the window size to be 6. And the embedding dimensions, I changed 96 to 48 just to make it run. So basically, I trained this model in Lightning Studio until I consumed the free quota. Then I trained it on Google Colab because I changed some parameters, and I downloaded the model and just reuse it here in code spaces. So here is the model, which I downloaded after training in Google Colab. The dataset I'm working on is STL10 dataset. It has 10 classes: airplane, bird, car, cat, deer, dog, horse, monkey, ship, and truck. All images are of size 96 by 96 pixels. All of them are color images, and the training set is 500 images, and the test set is 800 images. I didn't use the unlabeled images. I'm just using these two sets. I'm training on the training images, 500 images, and I'm testing on 800 images. So I'm downloading the STL10 dataset using torchvision dataset.stl10, and the split train will go into train set, and the split test will go into test set, and I'm creating data loaders out of these two sets of size 128. So here I commented out the training loop. I'll make sure that I'll remove the comments, but I commented out the training loop because I'm downloading the model, the pre-trained model that I trained in Google Colab. So I downloaded that, and I'm specifying the device for that pre-trained model to be CPU, because I trained in Google Colab GPUs. So I'm testing on the test dataset, and I'm getting 47%. Judging by how large is the test dataset, it's larger than the training dataset. So 47 of 800, it's almost half. So correctly classifying half of the test dataset makes me confident that the model has learned something, and I can move to the attention maps. I can test the attention maps. So now we trained the model. Now we are ready to create attention maps. The first step is to feed one image to the model and see how the model will react and and let's visualize the attention values. So here I'm creating a global variable, and just an advice, please don't use global variables. Global variables are hacky, they are messy, and they're very hard to debug. If you're debugging a code and there are global variables in there, this is your worst nightmare. So why I'm using global variables here? It's because that I didn't want to change anything in the Swin Transformer code. I wanted to be, if you look into this notebook and you look into the official GitHub repository of Swin Transformer, I want them to be identical. So I don't want to introduce any new statements into the code. So I had to use global variables. There were two thoughts in my head: is just to create a global variable or just write the attention matrices into files. So these are the two thoughts that came up in my head. So here I'm just fetching the attention matrices and putting them into a list called the global attention using the global variables. So the global variable, if I had to add some code to the Swin Transformer, I had to return the attention maps from this function, from this class, window attention, and I get it by the end of the model along with the predictions. But this would have, by doing this, I had to add some new statements into the code, and I don't want to do that. So here is the image that I'm feeding to the model, and here are the attention matrices. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 attention matrices. What are these 12 attention matrices? I'm using a model of size 4 layers, and the first layer has 2 Swin Transformer blocks, second layer has 2 Swin Transformer blocks, third layer has 6 Swin Transformer blocks, and the final layer has 2 Swin Transformer blocks. So this is the first 2 Swin Transformer blocks. These are the 2 Swin Transformer blocks in the second layer, and these are the 6, 1, 2, 3, 4, 5, 6 Swin Transformer blocks in the third layer, and these are the last 2 Swin Transformer blocks in the fourth layer. So first, let's understand what are these dimensions represent. 16, 3, 36, 36. So STL10 images are 96 pixels by 96 pixels, and we are specifying that the patch size is 4. So 96 divided by 4, we will have 24 patches along the height of the image and along the width of the image. And we are specifying the size of the window to be 6 patches. So 24 divided by 6, we will have 4 windows along the height of the image and 4 windows along the width of the image. And because in Swin Transformer the attention is performed between the patches within one window, so each window will have 6 by 6. So in total, each window will have 36 patches. So in the first layer, we are specifying 3 heads in the first layer. Think of the attention heads as the drawer cases. We will have 3 drawer cases. Each drawer case is 1 attention head, and each drawer case has 16 drawers. These 16 are the number of windows. Inside each of these drawers is let's say an A4 paper. No, A4 is not a square matrix. Let's say a square. If you open each one of these drawers, you will find a square matrix of size 36 patches by 36 patches. These are the attention values, the result of multiplying the query by the key, and these are the attention values, how each patch is looking to every other patch inside one window. So 16 windows, 3 attention heads, and inside each of these windows there is a square matrix of size 36 by 36. Think of this as an adjacency matrix that is contains the attention values, how each patch is paying attention to every other patch inside one window. Now this is for the first layer, for these two tensors here. What's the difference between these two tensors? The first one is a window attention, and the second one is shifted window attention. Now let's look at these two tensors here, 4 by 6 by 36 by 36. So because the Swin Transformer between layers, it performs downsampling, or they call it patch merging, the 96 pixels will become 48 pixels. So in the second layer we will have 48 by 48, and if the patch size is 4, we will have 12 patches along the height of the image and the width of the image, and 12 divided by 6, which is the window size, we will have 2 windows along the height of the image and the width of the image. So each window will have 36, will have 6 by 6 patches. Now we will have 6 attention heads, and because we have 4 windows, let's imagine that there are 4 drawers in each drawer case, and inside each drawer there is a square matrix of size 36 patches by 36 patches. And different attention heads are looking at different features within the image. So this is the attention values in the second layer. In the third layer here, these tensors, and these are alternating between window attention, shift to window attention, window attention, shifted window attention, and window attention and shifted window attention. So the size of this tensor is, again, downsampling 48 pixels, we'll get 24 pixels. 24 divided by 4 will have 6 patches, and 6 divided by 6 we will have 1 window to represent the image. Because we have 1 window, think of it just 1 drawer in each attention head. We have 12 attention heads in the third layer of the Swin Transformer, and we still have 36 patches by 36 patches. These are the attention values, the adjacency matrix, how each patch is paying attention to every other patch inside the window. So this is how do we get the shape of these tensors after passing one image. If we feed 2 images, this won't be 16, this will be 32, and this will be 8. So the first batch, the first dimension of these tensors represent the number of windows multiplied by number of images. To understand attention in transformers, here is a good paper that explains attention. This paper is called Formal Algorithms for Transformers. This document aims to be a self-contained, mathematically precise overview of transformer architectures and algorithms, not results. It covers what transformers are, how they are trained, what they are used for, their key architectural components, and a preview of the most prominent models. The reader is assumed to be familiar with basic ML terminology as simpler neural network architectures such as MLPs. And they have a nice quote here. A famous colleague once sent an actual very well-written paper he was quite proud of to a famous complexity theorist. His answer: I can't find a theorem in the paper. I have no idea what this paper is about. So here they are introducing the theories behind the transformers and how they are work. But I found the language is very clear here, and it basically explains the attention in a very good way. So attention is the main architectural component for transformers. It enables a neural network to make use of contextual information, e.g. preceding text or the surrounding text for the predicting the current token. It's a similarity between the tokens. The tokens here in the Swin Transformer are the patches inside one window. So algorithm 3 here, basic single query attention. E is the vector representation of the current token, a single patch that we're looking into. ET is the vector representation of the context tokens, all the other patches inside a window of a Swin Transformer. The V, the vector representation of the token in the context component. So query, it has its own weight and bias. For all T other tokens, they will be mapped into key, and they have their own weights and bias. And for all T in the value, they have their own weights and bias. And softmax is applied after multiplying the query with the key, and so they will be normalized by the number of attention heads. So algorithm 3 is the basic single query attention. Algorithm 4 is the masked, is the attention with a mask. Here is the mask, so the attention will be of the same value, and if it's masked, then the attention value will be minus infinity. And algorithm 5 is the multi-head attention. Here they are looping over all the attention heads. So the mask, you might be familiar with the mask in large language models, that the mask will be along the diagonal of the attention matrix, just to mask out the future tokens, to restrict the token to all the previous tokens, not the future tokens. But in the Swin Transformer, actually the mask is different. It has this shape. These patches will be masked out, just to move the window to the top left corner and leave these patches out. So these will be masked out, and they will be assigned, their attention values will be assigned to minus infinity. Actually, they didn't assign their values to minus infinity in the code. They assigned their values into minus 100. So inside Swin Transformer block, so this is the mask. The attention mask is minus 100. So I believe it's for computational efficiency. Minus 100 is more efficient than minus infinity. Another property of the attention matrices is that if you sum along the column dimension, all the rows will sum into one. That's because the softmax was applied to the attention matrices, just like what's written here in this spec. It's the softmax was applied to the attention matrices. So all the rows sum to one before they are multiplied by the value matrix. So now let's visualize the attention matrix in the first layer, the first window, and the first head. So these are 36 by 36 patches. You can tell that this matrix is not symmetric because of this, because of these columns. If we sum along the column dimension, we will have one column vector of ones, which is this column vector here. So what does this attention matrix tell us? It's that some patches are triggered by some patches. So patch number 11 is almost it triggers all. It has higher attention values with all patches inside this window. The same thing for patch number 20 and 22. They have higher attention values. So now it's up to us to make an image out of this attention matrix, because this is attention matrix. It's a squared matrix. but it should be a 6 by 6 window, and there are 16 windows in this Swin Transformer layer. But before we're doing that, let's visualize these values as histograms. So these histograms, I'm taking these histograms as the for each row this matrix. So I'm pulling these values and I'm just arranging them into a histogram. So you can see that most of the patches have attention values with the mean very close to 0.02. 0.02. But they differ in the maximum value. So for example, this patch has a maximum value around 0.05, but this patch has maximum values larger than 0.1. So by looking at these histograms, I found out that pulling the mean for each row would not differentiate these patches because they have the same mean. They all have the same mean around 0.02. So where they differ in the maximum value. So I'm pulling the maximum value from each row in this matrix, and hopefully the maximum value would represent that patch. This row is how the patch number 0 is paying attention to all the other patches inside within that window. So if I take the maximum value, and in this case it would be either this one or this one of these three values, it will indicate that patch is important within that window. But if that patch is not that important, just like patch 25 here, its value is diffused. So that its attention value is diffused across all other patches within the window. So I think, and I might be wrong, but I thought that the maximum value would be a good indicator where the patches are paying attention to. So this is the histogram visualization for the attention values, and here just wrote a function. It's called the plot attention, where I'm using the Windows reverse from the Swin Transformer GitHub repository to arrange the attention values into an image. The task is to transform this attention matrix into one window and do the same thing. So I'm pulling 36 values as a column vector, and I have to arrange it as a one window 6 by 6, and I have to arrange it in a way that it's all patches are mapped into their correct locations, so I can visualize it as an image. That's why I had a reshape test notebook. I'm just testing different reshaping strategy, different reshape, different views. So for example, if this tensor has 1, 2, 3, 4 stacked in front of each other, so 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 2 by 2 matrices, I want to arrange them as windows in a 4 by 4 matrix. So if I do reshape 4 by 4, it won't do that. It won't do it. It will flatten all these matrices as rows in the image. So I have to do this. I have to do permute, then I have to view it as a 4 by 4. If I do that, then I would arrange them as windows inside the matrix. So it will be 1, 2, 3, 4, 1, 2, 3, 4, and this permute and view is the same method that they used in window reverse function. Yes, here. Permute and view. So just I just wrote an explanation of what this plot annotation is doing. So the plot annotation function, I'm feeding a tensor of size 16, which is the number of windows, by 3, number of heads, 36 is the number of patches, and 36 is the number of patches. I'm taking the maximum along the column dimension, and I'm getting a column vector at the end of size 1 by 36. So taking the maximum along the row dimension, this should be column dimension. I should fix it, because this is where the value will sum to 1. So the maximum should be, taking the maximum should be the same, on the same dimension that where the softmax will sum to 1. So by taking the maximum, I will end up with the size of tensor of size 16 by 3 by 36. Now we have to reshape the tensor to 16 by 3 by 6 by 6. 16 windows of size 6 by 6 computed over 3 heads. And I'm not averaging over the heads, and I'm not taking the maximum of the head. I want to visualize each head separately. So this for loop will run over all heads. A tensor of size 16 by 6 by 6. By unsqueezing the last dimension, we will get 16 by 6 by 6 by 1. This is the required shape by Windows reverse function. So the Windows reverse function requires 4-dimensional tensor. The first dimension is the number of windows times the number of images, which is in our case is 16 times 1, 16. The window size 6, the window size 6, and the channel is 1, because we're feeding, we want to visualize an intensity images, just one channel. It's not the RGB. These are the dimensions of the tensor: 16, 6, 6, 1. To form an image out of these windows, we will have 4 windows along the height of the image and 4 windows along the width of the image. If each window is 6 by 6, the attention map will be of size 4. This is the number of windows along the height of the image times 6. This is the height of the window. We will end up with 24. 24 is the height of the attention map. Along the height of the image, we have 4 windows, and each window is 6 by 6. So we will have 24 patches along the height of the image and 24 patches along the width of the image, and we will visualize the attention value, the intensity of each patch. The Windows reverse function will first compute how many images in the tensor, because we only have one image. So it will perform this formula here in Windows in window reverse. Here, this formula, it will compute how many images in the 4-dimensional tensor. It will be 16 divided by 24 by 24 divided by 6 by 6. At the end, we will have b equals 1 image. It will create 5 dimensions. These 2 are for the how many windows, and these 2 are for how many patches inside each window. So it will permute these 2. It will be 1 image, 4 by 6 along the height, 4 by 6 along the width, and only 1 channel. So at the end, it will return a tensor of size 1 by 24 by 24 by 1. We will squeeze these 2, the batch dimension and the channel dimension, and we will visualize this image. So first I'm visualizing the Swin blocks with window attention. Then I'm visualizing the Swin blocks with the shifted window attention. So here is the original image. Here are the attention maps in the first layer. It didn't capture the main object, maybe here. But in the second layer, this attention map captured the main object in the image. And this one here. So I'm visualizing each head separately. In the first layer we have 3 heads. Second layer we have 6 heads. In the third layer we have 12 heads. The third layer, because of the downsampling, it got merged. But some of the attention maps still capture the position of the main object in the image. Yeah, this is for the window attention. For the shifted window attention, which is the odd indices inside the Swin block. See, these are the attention values after shifting the image. It's not that clear, just like the window attention, the shifted window attention. It's I can't see the object inside the shifted window attention. But what if we treating the attention maps as a troubleshoot the Swin transformer, what these attention maps are telling me that this Swin transformer needs more training. So I either have to increase the training epochs, or I made a mistake by decreasing the embedding dimensions from 96 to 48. So this is what the attention maps are, because these attention maps are saying that this Swin transformer is not properly trained, because it should be clearer than this, or at least I should see the main object in more attention heads. I tried to do attention rollout, but it turns out to be a failed attempt. So attention rollout is what's proposed in this paper, quantifying attention flow in transformers, and it's the same thing that they used in the original vision transformer paper. An image is worth 16 by 16 words. Transformers for image recognition at scale. In their attention map section, compute maps of the attention from the output token to the input space, figure 6 and 14. Here they are computing the attention where the transformer is looking. So we use the attention rollout. They are citing this paper, quantifying attention. Briefly, we averaged attention weights of bit L16 across all heads and then recursively multiplied the weight matrices of all layers. This accounts for mixing of the attention across tokens through all layers. But in Swin transformer, because of the downsampling, I cannot do the multiplication between consecutive layers. There is something I have to either decrease the size of the first layer or increase the size of the second, third, and fourth layers. So I tried to increase the size of the second and third and fourth layers and multiply their attention matrices with the attention matrices of the first layer. I tried to multiply it recursively, but first I have to match the size of the first layer, which is it was 144. So this is 36 by 36, 36 by 36, 36 by 36, 4 windows and 4 windows. I got 144 patches along the height of the matrix and 144 patches along the width of the matrix. So I tried to match this size for all the following layers. So this is the shifted windows. Now here, this is the second layer. Notice that I'm padding the size of each window to match the size of the attention matrix in the first layer. So I did that for all layers. Then I normalize and add the identity matrix and normalize and multiply. This is what's recommended by the attention rollout. But when I ordered the image, I got something that meaningless, which means that with increasing the size of this attention matrix, something went wrong, and I cannot visualize it this way. So this is why I called it a failed attempt to do the attention rollout. I'll make sure to remove this part of from the notebook before sharing it with you guys. So because I don't think this part would be useful to anybody, but I thought to myself that I could let's try this attention rollout, but it doesn't work out this way. That's it, guys, for today's video. If you find this video helpful, please like and subscribe. By the way, you can find a link to the notebook I'm working on in the description below. Thanks for watching. Bye.